Hey everyone, and welcome. Today, we're going to dive into something you use literally every second you're on a device, but probably never even think about: how data is organized. It's the invisible architecture that makes our entire digital world go round.
Seriously, just think about it for a second. You type a few letters into your music app, and bam, the song you want appears from a library of millions. How is that even possible? Is it just some supercomputer somewhere using brute force speed? Well, not quite.
You see, the real secret, the magic trick, isn't just about raw processing power. It's all about structure. It's about choosing the absolute perfect way to organize that gigantic library of music so that finding what you want feels instantaneous. And that choice? It's one of the most fundamental decisions in all of computer science.
So why does this all matter so much? Well, because choosing how to store your data, what we call a data structure, is kind of like choosing the foundation for a skyscraper. You get it right, everything you build on top of it is going to be solid, fast, and efficient. But if you get it wrong, the whole system could grind to a painful halt.
When programmers are making this choice, they're really balancing three key questions. First, what do you actually need to do with the data? Are you mostly searching it, or are you constantly adding and removing stuff? Second, what does the data itself look like? Is it just a simple list, or is it a super complex web of connections? And finally, you got to think about efficiency. How fast is fast enough, and how much memory can we afford to use?
To answer all those questions, programmers have this awesome toolkit filled with different structures, and each one is perfectly designed for a different kind of job. You can think of it like a carpenter's workshop, right? You wouldn't use a sledgehammer to drive in a tiny little nail. You need the right tool for the job. So, let's meet the main characters in this story, the key players in the toolkit. You've got your arrays, your linked lists, hash tables, trees, and graphs. These are some of the foundational tools, and trust me, each one has its own unique superpower. First up, the array. Its superpower is just incredible speed, but only when you know exactly where something is. It's just like a row of mailboxes, each with its own number. If you know the address, we call it the index. You can go directly to it in an instant. In the tech world, we call this constant time, or O of one access. All that really means is it takes the same amount of time to get an item no matter how big the list gets. Pretty cool, right? Then you've got the linked list, and its superpower? Total flexibility. This one's more like a treasure hunt, where each item holds a clue that points you to the next one in the chain. This makes it super easy to add a new clue or remove an old one anywhere you want, without messing up the entire hunt. Okay, so if every tool has a superpower, how on earth do you choose? Well, this is where things get really interesting. See, choosing a data structure isn't about finding the one best tool. It's about navigating a series of critical trade-offs. Let's look at three classic showdowns. First up, the classic dilemma. Do you need to find things in a flash, or do you need to be able to change your list on the fly, constantly making edits? This is the core problem that pits our first two structures against each other. And this just lays out the conflict perfectly. An array is fantastic if you just need to read data, especially if you know the index. But trying to add an item in the middle, you have to literally shift every single thing that comes after it, and that is incredibly slow. A linked list, on the other hand, just shines here. You need to add or remove an item? No problem. You just adjust the links, or the clues, between a couple of items. But what if you want to find the 500th item? Well, you have to follow 499 clues just to get there.
All right, let's look at our next trade-off. What if your main job is searching? You might think, okay, just grab the fastest lookup tool, right? But what if you need a very specific kind of search?
And here it is, that big aha moment. Have you ever wondered how autocomplete works when you're typing in a search bar? It's all thanks to a really specialized data structure called a trie. So here's the crucial difference. A hash table, it's a speed demon for general lookups. It uses a special function to find data almost instantly. It can give you a nearly immediate answer for whether a complete word exists. But here's the thing. It has no clue that car and carpet both start with CAR. A trie, however, is designed for exactly that. Now, its lookup time is technically slower. It depends on the length of the word, but it understands prefixes, and that makes it the perfect specialized tool for the job. Okay, for our final trade-off, let's talk about representing connections. Like a social network or a map of cities. The big question here is, how connected is your data? Is it a dense web where pretty much everything is linked to everything else, or is it more of a sparse network with just a few connections here and there? So this choice really comes down to two main ways of representing a graph. The V here stands for vertices. Those are the items, like people in a social network. And E stands for edges. Those are the connections between them. An adjacency matrix is basically a giant grid that keeps track of a connection between every single person. It's great for dense graphs where almost everyone is connected. But for a sparse graph, like a real social network where you're only friends with a tiny fraction of all users, it wastes a ridiculous amount of memory. And that's where an adjacency list is awesome. It only stores the connections that actually exist, making it way more efficient for space and for finding a specific person's friends.
So you're probably starting to see the pattern here, right? All of these specific examples, they all point back to this one single universal principle that governs pretty much every decision in algorithm design. It's the ultimate balancing act.
It's the constant, never-ending battle between time and space. Do you want your program to run faster, or do you want it to use less memory? The thing is, optimizing for one usually means you have to make a sacrifice on the other. Hash tables give you that incredible speed, but they might use more memory. Other structures might be more careful with memory, but then they take a little longer to do certain things. There's really no free lunch here.
So with all that in mind, how do you put it all together and actually make a choice? Well, it's not as scary as it sounds. You can follow a pretty straightforward mental checklist to get started.
You just start by asking yourself, what's my number one need? If it's blazing fast access by an index, an array is your go-to. If you're constantly adding and removing data, a linked list is probably your best bet. If your data has a kind of parent-child relationship, like folders and files on a computer, a tree is the natural fit. And if you're just storing simple key-value pairs, a hash table is almost always going to be the right choice.
And that brings us to the most important takeaway from this whole thing. There's no silver bullet. There is no single best data structure that solves every problem. The goal of a great programmer isn't to memorize one perfect solution. It's to understand the trade-offs and choose the right tool for the specific job they're trying to do.
So the next time you open an app on your phone, just take a second and think about the invisible structures holding it all together. When you're scrolling through your social feed, was it built to be super fast at adding new posts or at loading old ones? When you edit a photo, is that app built for raw speed or for the flexibility to undo all your changes? Every single one of them made a choice, a trade-off between speed and space, between access and modification. And now you know exactly why.